again we are going to solve another numerical example. How we find the numerically smallest eigenvalue using the power method. As in a previous lecture we say that in general normally we find a numerically largest eigenvalue with the help of a power method, but using the concept of a numerically largest eigenvalue with the help of a power method, we also able to find out a numerically smallest eigenvalue using the power methods. In a previous lecture we described the algo of a power method, how we find the numerically smallest element. Once again briefly we discuss about how we find the numerically smallest element. So first of all we define a matrix V. If lambda is a numerically largest element, we define a matrix B equal A minus lambda I. Then find the numerically largest element of a V, largest eigenvalue of a V, then numerically smallest eigenvalue of A equal numerically largest value of a B plus numerically largest value of A. This one is a algorithms, and how we find this one already we described in a previous lecture. So now how we find the numerically smallest eigenvalue of this matrix, matrix A equal 1 6 1 1 2 0 0 0 2, using power method if numerically largest eigenvalue of A is 4. Hence find all the eigenvalues. So how we solve this problem? Solution of this problem, as we know that in a power method, with the help of a power method only we able to find out a numerically largest eigenvalue. Now in order to find out a numerically smallest eigenvalue, we use the concept of how we find a numerically largest value using the power method, same concept. So for this we define a new matrix B. Let B be a matrix such that V equal A minus lambda I. A minus lambda I, where lambda is numerically largest eigen value. Numerically largest eigenvalue. If lambda is already given in the problem, then we use that value of a lambda. If lambda is not given in the problem, then using the power method, first of all we find the numerically largest eigenvalue. Using the power method we find the numerically largest eigenvalue, but in this problem already this is given, numerically largest eigenvalue of a is a given. So what is the numerically largest eigenvalue of A? Here this is a given, this one equal to the 4. So then we able to find out the value of a B. Once again I repeat this statement, if largest eigenvalue is a given, then directly we write this matrix. If largest eigenvalue is not given, then first of all we find the numerically largest eigenvalue with the help of a power method, then we write this matrix. So here numerically largest eigenvalue is already given, so easily be able to write this matrix. So now numerically largest value is a 4, so V equal A minus 4I. So now V equal, what is the value of A? A is a 1 6 1 1 2 0. 1 6 1 is the element of a first row, 1 2 0 be the element of a second row, and 0 0 2 be the element of a third row. 0 0 2 minus 4i 1 0 0 I with the identity matrix 0 0 1 0 0 1. Now, if we simplify this expression, the value of a B become, the matrix B become 1 minus 4 minus 3 6 1 1 2 minus 4 2 minus 4 minus 2 0 0 0 minus 2 minus 2. Now we find the numerically largest value of a B. Now, in order to find out, find the numerically largest eigenvalue of V, let x0 equal 1 0 0 be the approximate eigenvector corresponding to numerically largest eigenvalue of B. So, we find the numerically largest eigenvalue with the help of a power method. So, to apply a power method, we pre-multiplied by B in an approximate eigenvector. So, pre-multiply B in x0 So, what is the value? This, once we check this one, 433. So, now B is a minus 3, B is a what? B is a minus 361 and 1 minus 2 0, second row is a 1 minus 2 0, already this one become blank. So, 1 minus 2 0, so 0 0 minus 2, 0 0 minus 2, 0 0 minus 2 multiplied by the x0, B x0 equal, here multiplied by the 1 0 0. So, what is the value? Row by columns, the value become minus 3, minus 1, first row first column, second row this column, third row this column, minus 1 0. So, in order to normalize the numerically largest element, we take minus 3 outside, inside if we divide by minus 3 divided by minus 3, this become 1, minus 1 divided by minus 3, 1 by 3, 0, 1 by 3, 0. Now, if we simplify this, minus 3, 1, 0.3333 and 0. So, for the next iteration, we consider this become minus 3 x1. So, for the next iteration, what is the value of x1? x1 become 0.3330. So, again pre-multiply by b in x1, vector x1, then what will happen? bx1 become, bx1 equal, b is again minus 3, 6, 1, 1, minus 2, 0, 0, 0, minus 2, and what is the value of x1? x1 is a 1, 0.3330. So, if multiply first row by first column, the result become minus 3 into 1, minus 3 plus 6 into 0.33343, we write a 43 plus 0, this one is a first element, and second element is a 1, 1 minus 2 into 0.3330, and third one is a 0. So, after simplification, already here we write in the next slide the result of this expression 1 minus 0.333, here minus 0.333. So, minus 3, this one is a 1, sorry, this one is a 1. So, this one is a minus 1 by 3, this one is a minus, and this become what? This become so, if this become minus, then here this become minus, and 1 minus minus plus. So, what is the result? Result here already we write the result after solving this expression, minus 3 and minus 6. So, this become minus 5, minus 3 into 6, 6 3 is a 18. If we simplify this result, then this become minus 5, 1.666 and 0. After multiplying this result will occur. So, in order to normalize the numerically largest element is a minus 5. So, minus 5 here we take outside and divide all the element by the minus 5. So, the result become minus 5, 1 minus 0.3330. So, in a next iteration, what will happen? Here we consider the vector x1. So, this one is a vector x1, bx1 equal minus 5 x2. Now, what is the value of x2? Here this is the value of x2. This vector is a value of x2. Now, again pre-multiply by b, then bx2 become minus 3, 6, 1, 1, minus 2, 0, 0, 0, minus 2 into x2 with a 1 1 minus 0.333 and 0. If you closely observe this vector x1 and x2, both the vector have a same value, then after multiplying these two, this matrix by this vector, then the result again becomes same, minus 5, 1.66, 666 and 0. If we simplify, if we normalize this one and divide by the numerically largest element, then this vector become minus 5, 1, minus 0.3333 and 0. Now, if we closely observe, and here if we write this equal minus 5 x3. Now, what is the value of x2 and x3? x2 equal 1 minus 0.333 and 0, and x3 is also a same value, means x3 equal 1 minus 0.3333 and 0, 0, 0. So, now we stop the iterative procedure. Now, since x2 equal x3, thus ax2 equal lambda x3 equal lambda x2, ax2 equal lambda x2. This implies that x2 be the 1 minus 0.3333 0 with the eigenvector corresponding to numerically largest eigenvalue of V. And what is the numerically largest eigenvalue? The value of a lambda. So, what is the value of a lambda here? The value of a lambda is a minus 5. So, numerically now numerically largest eigenvalue of V equal what? Equal minus 5. Numerically largest value of numerically largest eigenvalue of V is minus 5, and numerically largest eigenvalue of A equal 4. This implies that, as we described in a previous lecture, how we find the numerically smallest element of A. If we add these two values, numerically largest element of a V, numerically largest eigenvalue of a V, numerically largest eigenvalue of A, then we able to find a numerically smallest eigenvalue of A. And procedure and methodology already we described in a previous lecture. So, here only we use the result. So, numerically smallest eigenvalue of A equal numerically largest eigenvalue of a B minus 5 plus numerically largest eigenvalue of a A. This if we simplify this expression, then minus 5 plus 4 become minus 1. So numerically smallest eigenvalue become minus 1, numerically largest eigenvalue become, numerical largest eigenvalue is already given 4. So last question that asked in this problem, hence find all the eigenvalues. As we know that the sum of eigenvalues of any matrix equal to the sum of diagonal elements. Trace of a matrix equal to the sum of eigenvalues. Trace is what? Sum of diagonal elements. Sum of diagonal elements. So in order to find out all the eigenvalues of a 3 cross 3 matrix, now numerically largest eigenvalue and let this one is a lambda 1 equal 4. Numerically smallest eigenvalue and let smallest eigenvalue is a lambda 2. And here we calculated the numerically smallest eigenvalue. Numerically smallest eigenvalue is a minus 1. And we know that trace of matrix A equals sum of all eigenvalues. We use this result. Trace of a matrix is what? Sum of a diagonal element. Principal diagonal element. Sum of a principal diagonal element. Equals sum of eigenvalues. And let third eigenvalue is a lambda 3. So lambda 1 plus lambda 2 plus lambda 3, because matrix A have a order of a matrix A is a 3 cross 3. So there is a 3 eigenvalues. So sum of a diagonal element of a matrix A is a 1 2 2 2 2 4 plus 1 5. So sum of a diagonal elements become 5 equal, what is the value of a largest eigenvalue? 4. This one is considered as a first eigenvalue. Second eigenvalue is a numerically smallest eigenvalue, minus 1 plus lambda 3. So what is the value of a lambda 3? Lambda 3 become 5 minus 4 and plus 1 equal lambda 3, and 5 plus 1 6 minus 4 2 equal lambda 3. So you may verify numerically largest eigenvalue is a 4, numerically smallest eigenvalue is a minus 1, and third eigenvalue is a lambda 3 equal 2. So 2. So in this way we able to find out all the eigenvalues also. Only in a 3 cross 3 and 2 cross 2 matrix, with the help of a power method, we able to find out all the eigenvalues using the power method. So using a power method, not only be able to find out a numerically largest eigenvalue, also be able to find out a numerically smallest eigenvalue in this way. If matrix is a 3 cross 3 matrix, then also be able to find out all the eigenvalues using the power methods. So this one is all about this lecture. In the next lecture, we try to find out the eigenvalues using the Gibbons methods. So thank you joining my lectures.